we're going to talk about anti-diuretic hormone, and you can see I've already started drawing for this video, and the main reason is because I'm not a great drawer and I wanted to make sure that everything was pretty clear. And so I drew out on one side the pituitary gland and on the other the brain. And so antidiuretic hormone, I underlined ADH because that's usually what it's called. People call it ADH. Sometimes people call it vasopressin as well. And actually vasopressin is good because it's useful. You can see vaso kind of refers to blood vessels, and pressin kind of squeezing down on blood vessels gives you a clue as to what the hormone is doing. So I've drawn for you the hypothalamus here, hypothalamus, and also right below it, this would be kind of the infundibulum, kind of the neck, infundibulum, and at the very bottom the pituitary. So this is the actual pituitary down here, and there's a front and back to this, and the front facing forward closer to the eyes would be the anterior pituitary, so that'd be over here, anterior pituitary, and back here this lobe would be the posterior pituitary because it's a little bit further back. And since we're naming stuff, let me just go ahead and round it out. This right here is actually the optic chiasm. It has to do with vision. So I'm just going to write optic chiasm so you know what we're talking about. And the only reason I even bring that up is because just above it, let's say in this area, just above it, and if I was to draw it over on my little diagram, that'd be like maybe right there, is what's called the supra, S-U-P-R-A, supra optic nucleus, supraoptic nucleus. The nucleus here just refers to a collection of nerve cell bodies, not the nucleus we usually think of, meaning not the one where it's sitting inside of a cell and kind of directing the flow of traffic and the brains of the cell in a way of seeing, but here the nucleus is actually just a collection of little nerve cell bodies, and I'm actually just going to draw two, but there's actually many more there. This is just for diagram purposes, and actually if I was to draw the rest of this nerve, it would actually go all the way down, and this is actually beginning to share with you some of the cool aspects of this hypothalamus and the posterior pituitary. You can see that basically these nerve cells start in one spot and they go all the way down to the posterior pituitary through the infundibulum. So this is how the hypothalamus and the posterior pituitary are connected through nerves. And these nerves are actually full of the hormone ADH. So we've already talked about the fact that this is related to ADH, but now you can see exactly how. ADH is actually being made in these nerve cells, and it's actually sitting here waiting for the right moment for these nerves to release it. And this ADH is actually a small protein. So it's actually a small protein, and it's 9 amino acids long. So it's actually pretty small. This is ADH. ADH. 9 amino acids. So it's pretty teeny, and it's a hormone. And if you know it's an amino acid based hormone, you can think of it as a peptide or a protein hormone and distinguish it from the steroid hormones. So this is how ADH is made. It's made in these nerve cells. And the next thing to talk about is how it's released. And so if you have, let's say, a little capillary bed in here with little arterioles and capillaries coming together into little venules on this side, what happens is that when there's a trigger, and actually maybe I should write that in a very bold color, let's say red. That's my favorite bold color. When there's a trigger, these nerve cells right here are going to fire off their ADH. They're going to release all that ADH, and it's going to dump right here into this area where all the capillaries are. And of course, the flow of blood is going to carry all that ADH into the little vein. And let me draw the venule in the vein, and basically take it to the rest of the body. So this is how ADH actually gets released out of the nerve cells that live in the supraoptic nucleus and gets out to the body. It basically does it by dumping into that posterior pituitary and getting picked up by all those little capillaries and venules. So I guess the next issue is to figure out what is the trigger. So what is the trigger for this little supraoptic nucleus that I've drawn here? So let's talk about that. Let me make some space. Now we've got a clean bit of canvas. So let's talk about the triggers that our body uses to know when to fire off that ADH to get it released. So the main trigger, and this is probably the one trigger that you want to take away, if you're going to forget everything else, try to remember this one. The main trigger is going to be high blood concentration. And the way we think about blood concentration is in osmolarity. Osmolarity. So let me write that down. Osmolarity. So what osmolarity refers to is if you took all of the solutes that are floating around in the blood, so that includes things like everything from like protein to sodium to potassium, everything that is going to drag water into the blood vessels, if you combine all that, then what is your total blood concentration going to be? And you can almost think of it as like a meter. So let me draw for you like a little meter here. So on one side you've got, let's say something like that. And on one side, let's say you've got 260, and on the other side 320. And this is just concentrations, right? So 280 and 300. And this is osms per liter. Actually, these are the units here. So osmolarity as measured in osms per liter. So this is the concentration, and what you want to do is you want to really stay in this area right here. This is kind of your green zone. This is where the body likes to be, generally speaking. And if it's here, if it's in this area, or if it's in this area, then that's where the body is not too happy. And so, for example, let's say you're in this first zone. This would mean that your body is noticing that the blood is too dilute. And if it's on this side, your body's noticing that it's too salty. The body is saying that the blood is too salty. And so in this case, if you have, let's say, like I said, a meter down here, if the needle is falling in this area, then that's going to be a trigger for ADH release. So that's the first trigger that we can talk about. In fact, why don't I even go back up and add that to our diagram. So I'm going to put that into our diagram so that we can see it very clearly as being one of the triggers. So let's imagine you have right here a little nerve cell, and I'm going to draw it this way purposefully because we actually don't know where these little osmoreceptors are. All we know is that they do a fantastic job, but we don't know exactly where these osmoreceptors are. And this is my little diagram that I drew before, and you can now think if the osmoreceptor is telling you that it's over there, then that's a problem. And in fact, why don't I even go one step further and label this as my osmoreceptor. Osmoreceptor. So if my osmoreceptor is set to tell me that it's too salty, that is one of the signals that's gonna trigger ADH release. Okay. So now, what's a second trigger? What's another reason why we might release ADH? Low blood volume. Low blood volume. Think about that for a second. How in the world would your body even know that the blood volume is too low? Well, let's go back to basics. Let's go back to the heart. That's where I like to begin because that's how I always think about it, is just very simply what is going into the heart and what's coming out. Well, we know we have blood vessels, large ones in fact, large veins, dumping into the heart, right? So we have the superior and inferior vena cava. This is the superior vena cava, this is a large vein, and this is the inferior vena cava. And these aren't the only large veins. but these are two examples of large veins. And we also have the right atrium, right? So we have a couple of spots here that are in the blood vessels where we might have little nerve endings. So nerve endings in these areas are going to start recognizing when the blood volume is low, because remember, the venous system, this is kind of a stretch, the venous stretch from something we talked about a long time ago, the venous system is actually going to be a large volume system. So if there's ever a decrease in the volume, that would be one of the best places to figure it out, right? So information in the walls, so basically these nerve fibers rather, in the walls of the vessels are going to be less stretched. And they're going to say, well, why are we less stretched? And the answer is that there's actually less blood volume. So when they're less stretched, they're going to send a signal and say, hey, something's up. We have less blood volume, and I think the brain needs to know about that. So that's how a signal gets sent all the way up to the brain. And actually, I can draw that in as well. So let's put in, let's say, a little receptor here. And now these are going to go down and sense low volume from those receptors in the large veins in the right atrium. Okay, now what's another trigger? You can see there are a lot of different triggers. I'm putting up one after another. Let's put another trigger up there. What's another reason why ADH would be secreted? Well, maybe a decrease in blood pressure. Now, we know that the veins tell us a lot of information about volume, so it might extend that the arteries can tell us about pressure. And you might recall from another video where we talked about baroreceptors that this is a fantastic way to get information about pressure. So let me draw some of those baroreceptors. And baroreceptor just refers to pressure receptor. And so we have baroreceptors that are in the aortic arch right there. And we also have baroreceptors that are in the carotid sinuses on both sides. So these baroreceptors are going to recognize when the blood pressure is starting to go low. And they're going to send a signal up to the brain to say, hey, again, we need to do something about this. Our pressure is low. So that's another signal up to the brain. And that we can draw in right here. We could say, okay, maybe something like this. And that would be a signal about low, let's write that here, low pressure. So now we've got signals about high osmolarity, low volume, low pressure. Are there any other signals that we can think of? And one more jumps to my mind. Angiotensin II. Angiotensin II. So you remember angiotensin II is actually part of the whole RAS system. This is part of the RAS system, the renin, angiotensin, I'll just write AT, aldosterone system. And so angiotensin II is actually going to be another trigger. So you can actually imagine through a blood vessel, you might have a nerve nearby, and this is going to trigger right here, this molecule of angiotensin, which has 8 little amino acids, is going to be a signal to that nerve that it needs to let the body know, or the brain know rather, that pressures are low. And so this is another signal. And let me just write that up here in our picture. So another signal could be something like this. Maybe right here. And the exact location that I'm drawing is actually just kind of arbitrary. But the idea is that you have angiotensin II having effects on the brain as well. And so this little molecule is going to come and let the brain know that, hey, even the kidneys are trying to do something about their blood pressure. And it would be great if the brain got involved in releasing some ADH if needed. So these are the different triggers. And like I said in the beginning, probably the main one you want to think about as far as ADH is concerned is this osmoreceptor. This is really the most important one because Everything else is secondary to that. That is definitely the major function of ADH.